Hello guys, very good evening to everyone, and I welcome you all to the OdinTalk session. And as you know that the topic of today's session is on applications of AI in cybersecurity. With our speaker, Dr. Mohit Sewak, who is a principal applied AI researcher at Microsoft. So yeah, good evening to our speaker as well, and good evening to you, Shruti ma'am. So I think you can go ahead with the hosting now.
Sure. Thank you very much. A very good evening to everybody, and welcome to another session of Odin Talks. If you're able to hear me clearly, could I have a yes in the chat, please? Could you just confirm if you can hear me clearly? All right, great. Um, we have with us Dr. Mohit Sewak. Dr. Mohit, can I request you to switch on your camera, please? Great. All right, so today's talk is going to be really interesting. Looking forward to it because we are going to bring together two areas that have been really popular these days because of its applications. One is AI, and the other is cybersecurity. And Dr. Mohit brings together these two and talks about how artificial intelligence can be applied in cybersecurity. So it's going to be a really interesting talk. Dr. Mohit, I'd request you to talk briefly about your journey in AI and how cybersecurity came to be your area of research, and then continue with your talk today. Over to you.
Great. Yeah, thanks a lot, Shruti ma'am. So let me briefly introduce myself and my journey into AI. So my PhD has been into applied AI, very specific to cybersecurity, and it has been into advanced AI, the things and areas like deep reinforcement learning, deep learning, computer vision, NLP. These have been like part and parcel of the advanced AI program for me. Currently, I'm the principal AI researcher for Microsoft Security, which stands in a point where the security and the compliance is like one vertical for Microsoft, which is called SCIM. So I started with a lot of applications of large language models into NLP and the compliance side of things, and also for the security into different platforms, starting from Windows to crossplay to which is Android and Linux. Prior to this, I have been working on the applications of AI for IoT or machine IoT. And before that, I have a good experience working with vision related models for e-commerce. So this has been my journey in AI. Security is very special to me. I started with security applications for CM based systems, which is security event management, in which you get a lot of real time events, and how do you use real time AI to manage those events and detect the signals from it. Its applications into insider risk management, and then went into a lot of different areas of security. And currently, the topic of my talk is also where I'm working on, which is in the area of malware detection. We'll be covering a lot of those areas in specifics in this talk for just an overview perspective, then I'll go deep dive into one of these areas. Thank you. Yeah, let me know if you can see my screen also.
Yeah, we can see your screen.
Okay. So this will be the agenda for my talk today, and I intend to keep this talk very customized to the audience in this particular session. So I might not be able to cover the entire area that I wanted to, depending upon what is the feedback that I'm getting, and I'm very happy to slow down or increase my pace depending upon how do you want me to do. Before I would actually move, I would cover the cybersecurity defense landscape, and then I'll try to juxtapose my talk. And if you're seeing from the title, the talk actually covers even within security, it has a focus on malware analysis and detection. And even from a platform perspective, this is Windows malware. So this is like tip of the iceberg for cybersecurity. But I will give you the entire cybersecurity landscape and maybe for different areas per se. This picture that you see over here corresponds to not a particular vendor, but a generic industry landscape as different aggregators combined ensure that. So on the top, we have managed threat detection and response. Now, this is like a Uber level enterprise thing. Some enterprise will not have it depending on their size, but I'll just rewind it by 1 more minute so that you can listen to what I spoke earlier. So this is the picture that we see on the top. We have managed threat detection and response. This is a component that you'll see mostly in larger enterprises. Smaller enterprises may actually have the components below it in different parts and parcels, but this is like the complete pieces for some of the larger enterprises if you want to come. Then within the MDR part, we have two different parts. One is intrusion prevention system that we call IPS, and then is endpoint detection and response, which is EDR. Within the intrusion prevention systems, we have intrusion detection system, and once they detect the intrusion, then different actions could be taken to prevent it. So the flow of signals will go from down to up. So intrusion prevention system would actually detect dropping malicious packets, blocking malicious sources, resetting connections, alerting CM-based systems. CM is a real-time security event systems for any of the networks or infrastructures. And once this intrusion detection system is installed, you will also have different types of intrusion detection system. It could be a perimeter intrusion detection system. Here, perimeter defines the area perimeter, the network parameter of your in-house versus your cloud or other networks that are being connected to. Then there's a VM intrusion detection system. So if you're running VMs within your cloud or within your servers at your place, those will require some protection. Then there is a host intrusion detection system. So if you have, like for this example, my host machine, that will also may have an intrusion detection system. But a larger component that we'll find in most of the researches or other areas where research in AI happens is around network intrusion detection system or NITS per se. Sometimes NITS and IDS are used interchangeably. So if someone is saying only IDS and they respond with respect to a particular part, it's mostly the NITS. In NITS, the application of AI is into either form of anomaly detection, and there are or network traffic pattern. Then there are non-AI systems also, something like a signature detection system in which the packets are brought and their packets by signatures is taken, and you come to know whether that packet is malicious or not, or from the network pattern also, the network pattern signature is taken, and you see whether the network itself is malicious or not. In this area, the MLDL system will mostly happen around network intrusion detection system. It could be an anomaly-based system, or it could be advanced ML AI systems like deep reinforcement learning, these sort of an application. We are not touching this area for this particular talk, so we come to the right-hand side of it. On the right-hand side, we start with the endpoint detection and response system. So EDR is, you can say, global level system for different subsystems. Its responsible is for investigating security incidents and restoring endpoints per se. Then we have within it something called endpoint protection platform. This is where most of your malware detection systems and other systems combine. So one bigger part of the chink is over here is malware detection system, but there are other parts as well. For example, if there's some data being leaked out of your system, that also sometimes is part of either EPP. Some of the larger organizations may have a different system for what is called as data compliance and data governance. In that case, although the system might be different, but that system might in turn give signals to this endpoint protection platform, or it may be the other way around, that endpoint protection platform is giving signal to data protection systems. Then using data loss prevention and endpoint protection, a lot of different insider threat protection systems are also powered. This is also somehow connected to this particular. And within data loss prevention, you also obviously require user privilege control and data and disk encryption, so that if there are some confidential data that is coming, it should be automatically encrypted. Now I'll come to the part where this talks focus, which is around the malware detection system. So earlier, what you used to call as an antivirus program on your system, the more generic form of it is called a malware detection system, because it deals with not only just viruses, which are very specific types of malware, but a lot of different other malwares. So we have anti-rootkit, anti-spyware, anti-adware. This is all classification from the first generation malware system. We'll go deep dive into and we'll try to understand what is the first generation class malware and the second generation malware. Then we have something called an advanced threat protection system.
So malware detection system may work mostly upon signature matching or other sort of a techniques. If an AI-based system or sometimes advanced AI-based systems are starting being used, those would fall under the advanced threat protection. And threat protection would require two forms. One is a threat detection. So you have to first identify there's a threat, and then you will also have to define what is an advanced threat. So I just named the generations of malware. So most of the second generation malware, which are more difficult to detect using conventional mechanisms, those would come under the advanced threat detection. And there'll be some advanced type of other malware like ransomware, which will also come under advanced threat detection. So one is the advancement of the threat, how sophisticated or complex or how impactful the threat is. Then the second is the mode in which it comes and how it is targeting a particular machine. So sometimes there are very high value machines and someone wants to actually bring them down or do some malicious activity on that. They may actually use a zero-day vulnerability of that particular platform, that is called a zero-day attack, or they may actually have multiple malwares being attacking that particular machine simultaneously, in which case it will become a swarm attack. So these are also the paradigm of advanced threat protection. So in this particular talk, we'll be focusing on this area, which is advanced threat detection, and we'll be talking about polymorphic and metamorphic malware, and to some extent, we'll be also talking about advanced attack mode protection, like the zero-day attack and the swarm attack. I'll take a pause and see if there are any chat comments or questions, and depending on that, we'll go to the next section of the slide where I'll be talking about the background and the preliminaries of threat Windows malware. Okay, so far I do not see any questions or comments, so I'll just go ahead. I hope my screen is still visible. So let's define what is this problem of malware. So malware is actually a conjoint of two different terminologies, which is malicious software. So if a software is there which has entered your machine without an authorization, you are not aware of it, and it is trying to do an undesirable activity, that is what you will call a malicious software. Obviously, there will be many software which are ill-designed, so they're supposed to do something, but it keeps hogging your memory and your CPU. But they are running because of your authorization, you are aware of it. Although there are undesirable activities, but it is also supposed to do some desirable activities. In this case, it is not a malware, it's a badly designed software. But we are talking about very specific malware software or malicious software which has entered your machine without authorization. The history of malware goes back to 1971, where an engineer named Robert Thomas at the Bible Broadcasting Network designed a software. He named that software as Reaper. And that software was designed just to showcase his knowledge about software systems and the pride he takes in actually designing these type of a system. But soon they started being used as a malware. And since then, a rat race has developed between the malware developers and the defenders. In fact, the very first antivirus program, that point in time it was called an antivirus program, not just a malware anti-malware program, but the antivirus program that came to as a defense for that particular malware Reaper was also named as Reaper right after that particular malware. Sometime back, the founder of the McAfee system, John McAfee, termed the problem of malware as a very temporary problem, and as per him, it should have been solved in 2 years. But now we understand that this problem is actually a very grave problem. It's a rat race between the two parties. One, the malware defenders will keep evolving and they'll keep developing better malware, which will be difficult to detect. And as malware defenders, it's our duty to upgrade our systems and software so that we can detect it. In the earlier part, it used to be about signature matching. So if you download a particular file, you compute a checksum of it just to see whether you have downloaded a complete file. The checksum is unique to that particular file. But of course, even in the unique systems, or which is called hashing system, there are different types of collision-based mechanism. So there is a system called SHA-based system, wherein the collision could be minimal and also it could be computed more efficiently. That is what we call a signature of a particular file. The signature could be evolved using different techniques. SHA is just one of them. Even within SHA, there are different techniques. But through any of the mechanism, if you can get a unique, you can say value for a particular file, that can be called a signature. And if you keep a repository of the signatures for all the malware that you have seen in the past and you keep matching it to the particular file that you are seeing in real time, that sort of a system could be as simple as called as a signature matching system. So most of the earlier system that we had seen used to be signature matching. Now the pros of the signature matching is, of course, once you find a particular file, it's very easy to get a signature of that file, and it's also easy to match an absolute signature. But of course, there are downsides also, because we have so many files, and if you want a signature matching system that works uniquely for those trillions or petabyte, trillions of files that you have just seen, you would require a very large memory space to even store them and keep them. Now we come to the evolution of malware. So although we think that malware is a small problem, but we see that the number of malware is actually increasing year over year and month over year. So recently we have seen the rate of malware evolution has actually crossed hundreds of millions, and some years we get even 170, 130, 150 millions of malware. To that extent, the total number of unique malwares I would say that we are sitting on, or known unique malwares that we are sitting, is over 1 billion. And when I say unique malware, there will be a lot of different copies of those malware that will have different signatures. We are not even talking about them. And this is actually a bigger problem. And once we go inside and see how these copies are made and how this could be differentiated across different devices to have a different signature, then we'll understand how grave this problem is. Also, we see that this disruption is actually getting more and more pronounced because of how we are moving from work from home economy to digital lifestyle, and we have now multiple devices that we have, right, from enterprise to consumer devices. We have mobiles, we have laptops, and each of this is actually a different platform or might offer different opportunities for malware developers to perpetuate an attack from. Earlier, with mobile devices coming into picture and people using more and more mobile devices, and most of the people who started using a mobile device for the first time are not as security literate as some of us might be. And there was a hypothesis that it's the mobile device that is more vulnerable to any of those attacks, and that is where this requires protection. A lot of workforce moved from server-based devices protection to mobile devices protection, but still we see like the Windows malware or the server-based malware are much more as compared to any of the mobile devices. The number one mobile platform from adoption perspective and the number of device perspective today is Android. If we compare an Android malware from the perspective of volume of known malware to Windows malware, we see like currently they are around 3% of the Windows malware. In fact, even at the peak when mobile devices were coming new people were coming, and it was very lucrative for malware developers to make malware for, it was right at even at its peak around 6%. So that is where this talk is focused more towards the Windows malware, but per se we can think of a session around Android and Linux malware also. Now let's understand some evolution of the classical ML and what it does for malware detection. So one problem that we see on the signature side of things, if we are trying to capture malware through signature, one is how many malware you can capture through signatures and how often those signatures would be updated, which is like more of a technical or engineering problem, wherein you might get in your updates for your anti-malware or antivirus program, and those updates will contain a lot of different new types of signature of the malware that has come recently. That's not a problem per se, but the bigger problem is once the malware starts evolving, which means that I have a base malware today, and with just slight changes to that malware, I can keep producing new malware. Now the problem with the signature matching thing is that they will do an exact signature match. So even if there's some changes even in the packaging of a particular malware, so if I zip a file, I unzip it, I zip it again, very likely the signature of that new zip package will change. Now this is a very random example of a zip. We do not do a malware detection at the zip level, we do it at a file level. But this is just to showcase how packaging, even slight unpackaging and packaging, can actually change the signature of a particular file. which means that even for a malware, if you do sort of a unpackaging, and just packaging and packaging is one operation, you can do like multiple types of operations in which without changing the malware, you can keep changing the signatures of that particular malware. And with changing of the signature, these malware-based systems, anti-malware systems which are based upon signature matching cannot work. That is where the role of machine learning comes. So there's now two sides of machine learning that I'll be talking about. One is what I'll be calling as conventional machine learning or classical machine learning. So I know you all are from a data science background. You might be learning about a lot of different data science applications and algorithms. So anything that is not into deep and advanced learning, the types that I talked about, reinforcement learning, deep learning, computer vision, NLP, or applications of deep learning models for computer vision and NLP. This is what I'll be calling as advanced right from now onwards. Anything before that, which is like your random forest, decision trees, even ANN, which is artificial neural networks, which are non-deep, will come under the conventional ML type of things, as I used in this particular talk. So the first evolution that we did was we started using conventional ML to detect this particular malware. And it has got a lot of success using conventional ML-based systems, but because of the things that we were just talking about, we'll see that even those conventional ML-based systems are not sufficient these days. If I am to come to the list of problems that we face today, even after the evolution in the computer, this conventional ML, these are the 4 points, which is the motivation for this particular talk going in. First, the changes that we see in the industry where malware developers themselves have become organized. So malware development is now no more thing of a particular person's hobby or a particular small group's initiative for either protecting their own state or acting on the purpose of the state or for particular lucrative reasons. But it's not full-fledged industry like you have in a corporate, like one department is taking about marketing, the second department is talking about mergers, integration, and so on and so forth, and financing. The similar thing is now happening into the world of malware. So some sophisticated malware like ransomware. Now these are perpetuated as ransomware systems, which means now there'll be some groups that will be doing an initial access broker development malware. Initial access broker is a type of malware that would be infused into your system or kept into your system, and they will open a backdoor for the other team who would penetrate into your system, take control of it, and try to do some other malicious activities till finally a ransomware is dropped. So there will be different teams or that will be working in conjunction, in collaboration with each other to compromise a network or a particular machine. So one trend that we are seeing is that this has come up as an industry. The malware development and attack system has come up as an industry, and we need more resources to deal with such complex and integrated structures. The second thing that we talked about is that signature-based techniques still are mainstream. Most of like 80-90% detection, you would say, that still happens through signature-based things. But because of all the techniques that we talked about, either packaging and more sophisticated techniques, which is called obfuscation. We'll be talking a bit more about obfuscation in the later slides. But obfuscation is a technique in which at the file level, you change something such that it is not recognized as that particular file. That something could be changing at the code level. You can actually have some blank spaces left in the code and recompile the particular code. You can add some comments in the code, or at the lower level when it comes from the high level code, which we write in. After that is the compiled code, and the compiled code goes into your kernel. At that level, it's called an opcode or operation codes. So at the opcode level, you can actually infuse something and then recompile it back. There are systems to do that. All of these are different ways of doing obfuscations. And with any of these very minor obfuscations also, the signatures will change. That is where that analogy that I used of packaging comes to the malware, how the malwares are designed and changed. So all of these signature-based techniques could be evaded with this. That is the second problem. The third problem, which makes this problem very complex, is the advanced mode of attack. So it's not about that now you are having one random malware and you assume that this malware one day will hit a particular machine, that machine will get corrupted, and somehow either I will gain something out of it, or for the fun of it, that machine is corrupted. It doesn't happen now this way. a lot of countries are fighting against each other, and a lot of their first line of defense nowadays is no longer your conventional weapons, but these are like your cyber systems that are being compromised, and one state actors can actually have another state actors defense mechanism being brought down with cyber attacks. So in these type of sophisticated attacks, not just one malware that is used, it's like not only complex malware, but also complex mode of attacks, like form attacks and the zero-day attacks. And next in the talk, we'll be talking about how Windows malware has evolved. We'll be talking about the polymorphic and the metamorphic malware. So this is the core challenge that we are facing, that Windows malware has become very, very complex for even conventional ML to detect, not just signature matching, but even conventional ML is not able to detect those type of advanced malware. The fourth problem that we see is like when we used to design systems with conventional or the classical ML, it used to take a lot of expertise to design even the features of it, not just the model, but even before the models, the features that goes into the model requires a lot of experimentation such that you can get a very good model which has a very good detection and also is very efficient to work with. Now, with the speed of evolution that this malware development industry is going through, these sort of systems are very expensive and very slow to develop. That is also where a lot of motivation of this following talks will come. So in this particular talk, we'll be exploring different types of advanced AI technologies and how they use them for different applications of malware defense. And we'll be talking about different types of AI technology, starting from RNNs, LSTMs, deep neural networks, reinforcement learning, deep reinforcement learning, and deep clustering for their applications. That is one aspect of it. But if you would have actually dealt and taken some sessions on deep learning, you would have understood, or if you have tried to deploy any of the deep learning models, you would understand there are a lot of different practical applications of doing a deep learning task in production or inferencing through deep learning networks. One of this is that they are computationally very expensive. So if you have to infer across billions or trillions of files, they're going to be very expensive, because not only you'll have to have those many machines, some more, but also these machines would require GPUs, which are much more expensive than the CPU-based machines. The second part is for the training also, you require much more humongous data than you require for classical ML. Sometimes it can be like 1,000 times more data if you're lucky, but most of the times it will be 10,000 or even a million times much more data for any advanced applications. And the third is, of course, which is very specific to security, is that the data that we use in security is very scarce, which means that we do not have enough labeled data to train these type of systems. So for example, compare this to a large language model. You can crawl the web, and from the web-based data, you can do the training of the models. Or it may actually require crowdsourcing based mechanism to even label those particular data, and you can also have supervised learning mechanisms to train your model. But in case of security, it requires a lot of efforts and expertise to label each and every data. And even with the expert knowledge, it's very difficult for anyone just to see a particular file and say whether it's a malware or not a malware. They would have to do a lot of operations, maybe detonate that particular file, see it in the sandbox, what is the applications, or go inside and read the code or some pseudocode of it to understand whether it's a malware or not malware. So it requires a lot of efforts to label each and every file, which will go into the training of these models. So these are the challenges that we'll be trying to solve in some of the works that we'll be seeing ahead. I'm not able to see the screen, but if there are any chat comments or questions that you have, I'll just take a pause for the moderator to let me know, and then I'll go ahead with the remaining part of the talk. Okay, so I'll go back to the presentation. So before I move ahead, I'll just touch upon very, very basic ideas upon the different areas of deep learning that we'll be using in this particular talk. this is in no way trying to do justice to any of these areas. But if you want to just connect the dots and get the very high level understanding of this area, these are just one or two sliders. Of course, I know you might go deeper into this area into some of your own courses, or we can think about something into these lines to go deep into. So the first area to be covering is like, what is deep learning? So according to Jeffrey Hinton, who is considered as the father of deep learning, they are computational models which are built into multiple layers of processing. And the key aspect of deep learning as compared to conventional machine learning is that most of the feature transformation happens within the model. So you do not require experts to actually tell you which feature is more important than the other and what goes inside the model. You can have your data and let the model itself decide which feature is more important for itself. And of course, the third aspect is that you can also have very complex non-linear features, which is not very cognitive even for humans to understand that this level of non-linearity can go into defining a particular output function from an input functions. There are primarily two different types of deep neural networks. One goes into the areas of sequential, and the second is into non-sequential. The ones that goes into sequential learning is the deep neural network, and one that requires a recurrent sort of a data architecture and requires a sequence of data, not the sequence of the architecture, is called a recurrent neural networks. Now we'll be talking about two different sequences. One is the sequencing of the architecture of the network, if it is in a straight line where one layer only feeds to another layer, which is a feed forward network. One is that sequence. We'll be calling it feed forward networks in this particular case. Then there's another sequence, which is a sequence of the data. How do you use it? Whether it's a complete sequence or it's like a one record. That is what we'll be using the RNN for. And then there are domain-specific architectures. For example, in computer vision, one type of architecture is very common, which is called a convolutional neural network, which is a 2D space architecture in which you do not have a vector, but you have like a tensor of 2 dimension. And that tensor can actually go into different layers. So we'll be talking about all of these later on, but we'll be starting with DNN. If you can understand this, maybe at least one part of the area will cover up very quickly. So the first deep learning model that we'll be talking about is called a multi-layer perceptron-based deep neural network. In this particular model, you have this as the input layer, then you will have n number of hidden layers. This could be 2, this could be 3, 4, 5, 6, depending upon application. You can keep increasing this number of hidden layers. And most of the magic happens in this hidden layer. The aspect that we're talking about, that the deep learning networks will automatically create the best features that it's required, happens into these layers. And then finally, you have an output layer. This output layer will give you the prediction. So if your prediction is something like a binary prediction, whether it is yes or no, it will have only one unit. If it has a multi-class prediction, it will have as many units as the number of classes. So for example, in this particular case, we are just interested in knowing whether it's a particular file is a malware or not malware. This output will have only one node, which will give either 1 if it is a malware or 0 as an output if it is not a malware. Whether on the other hand, if we are interested in knowing which type of malware it is, and we have like different types of malware design, then it can have those many number of nodes in the last layer. Now we will be talking about 3 different concepts which we'll be using interchangeably in this particular talk. One is the activation function, loss function, and the optimizer algorithm. Let's come back. Now, if you see these arrows, each of these arrows will have a particular weight, which signifies that from an input to a particular node, once a signal is going, how much you should wait to. So this particular node may be connected to all of these input nodes, in which case it will have a weight for each of these connections. So suppose the value of this output of this particular input is A1, this weight is W1 at this particular node, and A1 into W1 is coming from this particular node. Similarly, it will be coming from all of these nodes. And this goes into a matrix computation sort of a mechanism in which the input to this particular node, after combining from all of these input nodes, will be something like A1W1, A2W2, A3W3, and so on and so forth. And there'll be some biases that we attach to these nodes. If this is the input, then the function that will convert this input to an output, which is coming on this particular node, which is the output from this particular node, is called an activation function, in simple words. Then the second part that we saw was a loss function. Loss function is very similar to your classical machine learning loss function, which is like once this network is being trained, what is that particular function or that particular loss that it's trying to minimize. So in case of classification, the example that we gave is most common in malware detection. It's mostly a cross entropy loss, but there are other losses that you can go to. In case of linear regression based systems, it's mostly linear loss or some other loss that comes into the linear category. Then the third part is optimization function or optimization algorithm, which determines what is the most optimal way that you should be training this particular network or these weights. The whole objective that we have is to train the weights of all of these components. What is the most optimal way in terms of the both computational cost also and other parameters like overfitting per se, to train this particular network. So how I should be updating each of these particular node with every iteration of training, such that I train it in the fastest and the most optimal manner to get the best accuracies and best efficiencies out of this. Next architecture that we'll be talking about and we'll use in this particular talk is called an autoencoders. Now, autoencoders are used to transform the input feature. So we talked about the deep learning can do it automatically, and even if we give it to the deep neural network, so your raw features, to some extent it will automatically create those features. But to make the task easier for the deep neural network, and if we want to have different classification algorithms working in parallel, we would actually segregate that layer of feature transformation a bit earlier in the settings, and we'll have some sort of a feature creation program. In classical ML, you might have heard about principal component analysis or SVD. These are the things that are used for feature transformation. In deep learning, we use a terminology called embeddings for algorithms like CNN and RNN. Those are very specific to those particular type of tasks, but a generic type of feature transformation that goes into multiple things is what can be used as autoencoder. In autoencoders, there are different types of autoencoders. What we are talking about specifically here is tagged autoencoders. We'll not go into details of the type of autoencoders for the sake of brevity. But in case of tagged autoencoders, our objective is, can we have a lower dimension representation of the data, which can work almost as good as the higher order raw data that we have. Suppose this is my raw input feature. So for the purpose of this application, assume these are the features that you have got from a particular file that you want to detect. And these features could be, say, 10,000 features. Now, you do not want to work at the level of 10,000 features, because then you require a very large neural network to deal with them. And also at this particular level, these are sparse features, which means that you will have for each of this feature a yes or no, whether this feature exists in the file or not exists, or you'll have just one particular value of these features. So these are called sparse features. Whereas what we want to use in the final model is this particular layer, which is called a bottleneck layer or a feature layer. So this will have much lesser number of neurons in this particular layer. So if we started with 10,000 neurons over here, maybe this layer will have only 64 or 128 sort of neurons. And this will have a much denser representation of the data. Now, the good thing about deep learning is it works very well with dense representation of data, but it doesn't work so much well with many number of dimensions of the data. So with this architecture, we, number one, reduce the number of dimensions in the data. Number two, make them a denser representation. And how this is done is, instead of just keeping this part of the network, which you are going to use finally as an input, we mirror image this part of the network into the output side. So what we do is, if we have like kept 10 different encoder layers, a bottleneck layer, we'll copy these number of encoder layers into a decoder layer. So we'll have 10 different decoder layers also in the same order. So if these layers have been coming down as 10,000, then 8,000, then 6,000 is the number of neurons. We will mirror image that into a reference order. So it will be 6,000, then 8,000, then 10,000. And then finally, we will have the output layer, which will be a mirror of the input layer. So if my input layer had like 10,000 neurons, this output layer will have exactly 10,000 neurons. And I will train this network in such a way such that if I bring it down from say 10,000 to say these 64 or 128 neurons, and then I expand the information from this 128 or 64 neurons back to 10,000 neurons, what is the loss between my output and input? And the whole objective of my training would be that this loss is minimized. Now think about it conceptually. If I can upscale my information from say 128 neurons to the 10,000 neurons, and it captures almost same amount of information as it had in my 128 neurons, which means my 128 neurons is the perfect representation, perfect dense representation in a very small dimensional space as it was in my original 10,000 neurons. So this is the whole idea of these type of autoencoders. It tries to compress their data without having to bear much losses on the data. And then once this network is trained, we'll remove this part of the network, which is the decoder layer and the output layer. And the output from the bottleneck layer, which is this particular layer, will start going inside your deep neural network or other neural networks. So for example, now this input layer, earlier this had, say, suppose 10,000 neurons, which was coming from the raw files. If we use this type of an architecture, from 10,000 neurons, you can bring it down to 128 neurons or any number of small number of neurons. And it is this particular thing that we're using instead of this input layer. So the size of the final network that is going to happen after it, which will have much lesser neurons because now it is getting information from lower order, lower dimension inputs. And then the whole size of my network will go down. And because of my size of network has gone down, I would require that much less computation. In fact, that much less data for me to optimally train this particular network. So this is the benefit of this type of networks for feature transformation. Then we'll be talking about a different type of deep neural networks where we will have information flowing into non-sequential layer, in which the data we'll be talking about is not at a one particular time span, but it will be coming into sequences, and those sequences is what will actually go into these networks. I'll not go much into depth of this particular architecture. This will take me some time. But once we come to it, we'll actually can have a separate session which will go deep inside these LSTMs and RNNs. So the base we have the recurrent neural network, which is now known as the family. No one uses the RNN architecture per se, the original one. But there are different architectures which are based upon the RNN. Some of them are LSTM, which is long short-term memory. Then we have something called a GRU, gated recurrent unit, and there's another called eco-state networks that is very popular in security. We'll be talking about them without getting too much deep into the architecture side of it. But the idea of this as compared to the previous DNN that we saw was that in DNN, irrespective of how the data was originated, you have to bring them at a particular non-sequential state per se, and then that will be consumed as it is. Whereas in this particular architecture, the sequence of the data is maintained. So for example, if you're talking about, let me give an example from a language perspective. So these words that I said, they have a sequence. And if you see these words in the same sequence that I'm speaking, you can actually to some extent predict whether it's a right sequence or a wrong sequence from an English language perspective. And maybe from the sequence, you can also predict what is the next word going to be, or you can at least have some idea of what topic I'm talking about. But if I jumble up this particular sequence and I actually just present you the dictionary of a particular words that I spoke, and I tell you like what was the frequency of the different words that I spoke, maybe just seeing those frequency maps, you can come to know what topic roughly I'm talking about, but you will never be able to understand the exact language that I spoke about, or predict the next words or the next topics in the language, because that sense of sequence itself is lost. So these type of RNNs preserve the sense of sequences such that you can do more complex things around it. In the context that I explained, I used the example of spoken languages in terms of malware. the actual code, the language is written in the high level code, or the compiled binaries that we talk about, that can also be sequenced. The example that I'll be giving you in this particular talk will be on the operation codes or the opcodes. This opcodes is after the compilation layer when it is tuned to a particular kernel. Each kernel will have some set of instructions, and when you put a sequence to those instructions, as you tell to the processor, that is what is called an opcode. So the sequences that we'll be talking about will be the sequence of these opcodes that we'll be trying to analyze using these technologies. Then we'll be talking a lot about reinforcement learning, and to be more specific, deep reinforcement learning. There's also a book that I had authored. In the case of deep reinforcement learning, there are some papers also that will go deep inside it. So I'll not go very deep inside it, but for the purpose of distinction, there are two different types of reinforcement learning. One is called a value-based reinforcement learning. The second is called a policy-based reinforcement learning. For the very starters who do not know about reinforcement learning, just let me give you a brief background. So essentially, earlier there was two types of machine learning. One was called a supervised machine learning. The second is called a unsupervised machine learning. Supervised machine learning is when you're trying to predict a particular thing. So for example, in the example that I gave, if I'm predicting whether it's a particular file is a malicious file or a non-malicious file, that is called a prediction, and that will come under the area supervised machine learning. Or even if I'm saying like which type of malware it is, if I have to choose which type, then also this will be a supervised machine learning. On the other hand, the type of applications that I spoke, where we are just doing a feature transformation, or we are doing something like a clustering that we're talking about, where we do not know the actual label of the file and the systems are not trained on the label of the file, but the system are trying to give me more information about the general distributions or the general file systems themselves, or they are being used not for humans but for some other algorithms to get them more information about a particular file. Those things will come under the unsupervised machine learning category. There's a third category of machine learning which is not much talked about, that is called reinforcement learning. Reinforcement learning sometimes is classified under approximation or you can say optimization based techniques, and sometimes they are a technique of its own because of its more proximity towards the AI side of things. In reinforcement learning, you try to train an agent such that it can take an learn an optimal policy. Now, when I say policy, that has a very specific meaning in terms of machine learning. So a policy is a set of actions that you will take depending upon the scenario that you are presented with. So suppose you are driving a car, okay? And in this particular case, assume it's an autonomous car. Now, everything that goes inside the learning of how do you drive the car in the different scenarios is called a policy. So when I have to apply the brakes, when I can increase the speed, when I can decrease the speed, when I have to turn the steering left, when I have to turn the steering right, when I have to maintain the speed, and so when I have to start the indicators, all of these will be different actions that you can take. When you'll be taking these particular actions will depend upon the scenario. So if there is a car in front of me, that car has slowed down, you should also slow down, and when the car has stopped, you should also stop. When everything comes, you start slowing down the speed. All of these are my different actions within the policy. So a policy could be the different set of actions and when you should be taking which particular action. This is a very simplified high-level example that I'm giving you, no way accurate, but just to give you a sense of what is a policy. So there are two ways that you can reach this particular optimal policy. And these two ways define what type of reinforcement learning that you are using. The first example that I have is a value-based reinforcement. In value-based reinforcement learning, you see the end state that you're going to reach and what is the utility value of that end state. So for example, now in the autonomous car example, suppose someone has come in front of me. I start giving points to my optimal scenario. In this, my most desired scenario would be that the car should immediately stop in this particular case. There could be other actions also that you slow down. There could be other actions like you keep continuing your pace. Some more actions, you take a left, you take a right. And based upon these outcomes, I start giving it some of the utility points. Now, in this particular example, I'm just giving it a random utility points, but all of these are more scientifically designed into a real application. So suppose in this particular case, I say that if you stop the car immediately, if someone has come in front of you all of a sudden, I'll give you maximum number of points. So suppose 100 points I'll give you. Whereas if you slow it down, I'll give you say 20 points. If you take a left turn and right turn or right turn to evade that particular person, I'll give you 4 points. If you do not do anything, maybe I'll give you a negative point, and if you hit the person, I'll give you minus 10,000. So this way, I'm defining the value of each of this particular state. In this particular case, the reaching of a particular scenario is called a particular state based upon the actions that you have taken. So I do not know what actions you're taking, but the state that you have reached, which is in this particular case stopped state, has the maximum value. If I start giving points based upon the final state that our agent has reached, irrespective of how it has reached it, then this is called a value-based reinforcement learning, in which I do not know what is the utility of a particular action, but I know the utility or the value of a particular state that I want the agent to do. On the other hand, there is something called a policy-based deep reinforcement learning. Policy, as I described, is actually the trajectory of state action sequences that an agent will reach based upon what it wants to apply on in a particular sequence of things. Now, the whole idea of training a deep reinforcement learning or a reinforcement learning agent was to learn an optimal policy. So in that particular case, a policy-based deep reinforcement learning is a more direct application of reinforcement learning. But as you may have understood from the definition, even to define a policy is very difficult, whereas it is easier for me to give values to the end state, but from a human perspective, and even from mathematically, you will understand, I'll not go into the deep of the mathematics per se. That is there in my book, and we can take different sessions for it. But to mathematically define a policy is very difficult, and to converge it is even more difficult. So this type of reinforcement learning, although is direct, is difficult to train, but it can deal with a lot of different complex scenarios. And the type of scenarios that we will be talking about are more complex to be dealt with value-based reinforcement learning. So the type of reinforcement learning invariably in the example that we are going to see next will be policy-based. Whereas for most of the applications that you would have heard about reinforcement learning, is you would have heard about AI being used for reinforcement learning. Most of you would have heard about say computer games or other games that would have heard about, even the game of Mario, Atari, and other things. Most of these uses value-based reinforcement learning. And in fact, to be more precise, if this data is coming from image, so suppose if a real-time agent is playing a game of Mario or Atari, these would be coming in the form of, the input will be coming in the form of video frames. In that particular case, they'll be using the input in the type of the deep neural network that we talked about, which is convolutional neural network. In that case, it will become a deep reinforcement learning instead of a classical reinforcement learning. But we'll be not dealing with value-based reinforcement learning. We will be dealing with policy-based reinforcement learning, because our use cases that we will be understanding this will be more complex. Then another area of deep learning advanced that we'll be talking about is deep listening. This is a more evolving field of research. This is not very much defined still upon. It's very new in the research domain. To speak much about it, we have to first, I think most of you will be knowing about clustering from a data science background, but clustering is a type of unsupervised machine learning in which you try to cluster or group the data points based upon certain patterns in the data. Now, in supervised machine learning or in classification also, you're doing a grouping of the data. So for example, I talked about whether it's a malware or it's not malware. There are two groups. One is group 1, one is group 0. But the only difference between your supervised learning or classification, in this particular case in clustering, is that in supervised learning, you know what these groups mean, and you consciously want to get to that particular right group of data. And based upon your early understanding of the group, because of the labels that you had in the data, you can reward your algorithm based upon the right prediction versus wrong prediction. In clustering, you do not know what the groups are, but you want to understand the data, and to understand the data, you want to see logically from the attributes that are given or the columns in the data that is there, what is the right combination that will automatically group the data into very specific number of groups, if you know how many groups you are interested in, or sometimes how many groups intrinsically exist in the data per se. Now, this analysis that you do can be used for your own understanding. Like if I'm doing a market analysis and I have like some demographic data, I want to understand, like for example, uh, the students of OdinSchool, they want to see like what are the different types of students, such that they can define the different training programs for each of the group of students. They can use clustering to determine those groups of students. Or sometimes they already have like training programs that are targeted, and they want they can only have like 4 different groups. In that case, they can determine that we have only 4 clusters. Let's see who comes into which type of clusters, and then based upon understanding of those clusters, going inside those clusters, seeing what is the commonalities in each of those clusters, they can define that this is the right training program for this type of cluster. But you do not force classify into the things that you already know. Now, clustering has been used very much for different applications that I talked about, and different applications of AI in cybersecurity. But what we are talking about here is deep clustering. Now, there are a lot of different problems in classical clustering. One problem, again, is the load it can take and how scalable it is. But the major problems to that is to the similar things that we talked about in case of deep neural networks is, number one, you require an expert who understand the data and the outcomes to actually even make the features that will go inside the system. Now, in most of the security related applications or more data scenarios where you have enough data even outside of security, you do not know what is going to be the right feature transformations or the right features that should actually go inside those things. The second problem is clustering is very sensitive towards the type of algorithms and the outliers that is coming in the data. So I will not go deep into the different types of clustering techniques, but now we started with, I think the most common names in clustering that you might be knowing about is k-means and hierarchical clustering. Many of these applications, you will see like a lot of different other types of clustering, for example, noise-based clustering, spectral clustering, kernel-based clustering coming up. Each has its own role. And that is where seeing the type of scalability issues and the noise issues that we have, specifically for the areas where the data is not so cognitive. A new field of clustering that is coming is deep clustering. And we'll be talking about this also in a lot of different novel applications that we have done from this particular art. Now I'm going to the next section of my talk, but before I go there, I'll just check if there are any questions that you can take or any suggestions on the speed. Is the speed fine? Can I go with the same speed, or you want me to go deeper, slower, faster?
Any questions from the audience so far? If you have any questions, please feel free to type it in the chat box, in the question Q&A box. Any of these concepts that were discussed, if you want a simpler explanation or you want to understand them in more detail, please feel free to ask.
Okay, I'll move ahead. I do understand I have 30 minutes left, so I'll plan some other session to go deeper into each of the sections. Now, there are 4 to 5 sections after this. I'll be covering one of these sections of applications of AI into malware detection. We'll be covering like the next 4, it will be some other discussion. But before I go into that, I'll cover some part of what is the malware and what we're trying to do, such that you can relate better to why we have to do what we have done. So as I explained earlier, malware will have different levels of complexity. So sometime back, we used to just classify the malware by its basic action or the objective that the malware tries to achieve. For example, if a malware is just trying to create a backdoor for someone else to take the control of your keyboard, and that someone will actually, using the remote access to your keyboard, will steal your passwords or type some commands and so on and so forth, that is called a backdoor. And then someone would, some malware that comes into during the boot times as to attack your the root notifications or the root of the backup process, those would be called as rootkits and so on and so forth. So most of these classifications, the first generation, was based upon what action the malware is trying to take and how it's trying to harm you. But now we recognize that this classification might not be optimal, and from a perspective of defense, it should be based upon how complex the malware is. Most of the earlier generation malware would be a direct malware, which means a program that would be inserted into some of the other software that you might have got or through some of the email attachments or the purposes. Whereas the second generation malware would be more complex in terms of the identification of this malware. So the second generation malware comes into four different forms. One is an encrypted malware, and it's very simple. So if I take a file, I encrypt it. So for example, now if suppose you give me a document that has some words into it, say A, B, C, D in this particular sequence. Now I start saying I'll not call A anymore, but I'll call it, say, suppose number 1. And I will not call B as B, but I'll call it as number. So I change this document which is saying ABCD to 1, 2, 3. This at the more basic level is called a ciphertext, which is like a text represented in some other form of text. A more complex form of hiding this information would be encryption, which would do a similar sort of a thing, but into a more complex algorithm, such that you can also reverse engineer that algorithm. So a lot of information that you see that transfer or happens flows through the internet, of course, at a level of secure channels, is through encrypted information. You might have seen your website. Some of the websites start with HTTP : // Some of them would be HTTPS : // Now that S stands for your secured websites, which uses encryption to transfer the information, such that even if someone tries to leak out the information through somewhere between your final origin and your destination, someone would have like access to your network or some other thing. Even if they get the information, they'll not be able to use it because in the tunnel that is between origin to destination, it is encrypted. The similar thing happens with malware also. So with every attack, the malware can actually encrypt itself. And once the malware encrypts itself, now since the earlier system for using signature matching, the signature of an encrypted malware, despite the fact it is the same as the original malware, will be entirely different. The signature will be different from the original malware's signature. So people or malware developers started using this sort of encryption of malware to evade a signature matching based techniques. But the problem with this is that you can actually have the signature of the encrypted malware also. So if I'm using a particular encryption key, I know that this encryption key would actually change this malware to this particular state. So for that particular state also, I'll get the same signature and I'll put it into my signature database. So my signature matching can also be detected in this particular. So the malware developers became more smart and they started using something called an oligomorphic malware. So oligomorphic malware is also a type of encrypted malware, but it will not have one signature. It can use different decryptors to actually encrypt the malware into different form and also then decrypt the malware into different forms. So now for one particular malware, you do not have one particular signature, but you can use different decryptors to have different encrypted malware of the same malware. Now that is when the malware defenders also started analyzing this pattern, and instead of then trying to detect the malware itself, they started detecting the decryptors. Now, since the decryptor was not changing, so irrespective of which malware trying to encrypt, sort of things became simpler because you can have like 20 different malware instead of identifying those 20 different malwares. If you are using as a malware developer, if I developed a decryptor, I'd like to use it for different malwares. So instead of as a malware defender, instead of detecting the malware, I started detecting a decryptor, and I used to just flag that particular file, and then that could be blocked from entering your system if I detect a particular thing. That is when the two most advanced form of malware, which is a polymorphic malware and the metamorphic malware, were designed by the malware developers. So what happens in polymorphic malware is the decryptors are changed using the techniques which I described as forms of encryption-based technique, which is we call it as obfuscation. So basically, the decrypted code itself could be now changed using techniques of changing the code or the memory allocation systems or other systems, such that now the decryptor couldn't be identified anymore. With every attack, there will be some junk opcodes or junk codes inserted inside your decryptor, such that it obfuscates into a new. So now the fight comes back to again identifying the malware, and we had to identify each and every malware as different form of oligomorphic malware. Although signature matching couldn't be done, but you'll have to use a lot of different machine learning to identify. That is where the most complex form of malware, which is called as metamorphic malware, started being developed by the malware developers. In this, the same technique that we were using for the decryptor failure of oligomorphic, now this is starting being used to the malware. And depending upon how many malware are, you could have n number of metamorphic copies of the malware by changing or obfuscating those malware at the code level. At this level, it becomes so complex that even most of the classical machine learning based techniques that we have are not able to identify different variants of metamorphic malware, even if they are coming from the same file that a particular uh, malware defense system would have seen earlier. And most of this talk would be focused towards identifying these type of advanced malware and why we cannot use the type of classical machine learning that we have been using earlier, and why we need deep learning and other forms of advanced machine learning. This is like the history of how different types of machine learning started coming into picture to detect malware. I'll not go deep into that. Maybe once if we plan something like a workshop sort of a session to use different types of machine learning for malware detection, we can have some insight from it. But I'll skip this slide for now, and I'll come directly to the evolution of deep learning based systems, and that will help us go through the first section of malware defense. So deep learning started being used in malware detection from 2015 onwards. So where we have seen like the MLP DNN based systems being used for malware detection, and using it like a lot of high detection rate, which is like 95% of recall started being shown at 0.1% FPR. For those who do not know about this terminology, recall is something about if you have 100 malware, out of those 100 malware, how many malware you're able to detect, that is called recall. That 100 malware could be coming to you in the form of, say, benign files. You have 1,000 benign files. In those 1,000 benign files, you add 100 malware. And I'm not talking about how many of those 1,100 or 1,100 files you were able to detect correctly, but I'm very specifically pinpointing towards how many of those 1,100 files you detected as malware were actually malware. That is will be called as a recall of my particular model. And in this particular case, we are biased towards the positive side. We are fine to, I'm not saying that we are fine to block a particular benign file that again goes into false positive, but we cannot let any of the malware pass through. And that is where this specific terminology of recall is important from a security perspective. This is again a data science terminology you'll see everywhere, but here many of the things that we will listen to will be either in the form of recall or the false alarm rate, or which is also called a false positive rate. So the other terminology that I described was, suppose there are now 1,100 files. In most of the cases, your malware will be very few, your benign files or non-malicious files will be very high. But I tune the model such that it is able to identify each and every malware very precisely. What will happen to that malware model is sometimes it will also make a mistake in calling a benign file as malicious file. That is what we call the false alarm. And the rate, which is like out of 100, or how many of them are, rate will be out of 1 if you just divide by the total number of files. But if you add a percentage, that will be out of 100. So out of 100, how many of the are false alarms? That will be called as the false positive rate. If it's just a rate, there is no number, just consider it out of 1. If there's a percentage out of it, just consider it out of 100. So in this case, 0.1 percentage means that out of 100 files, or out of 1,000 files, like 1 was the false alarm, this particular case. Then in the same years, similar studies started happening on the recurrent architectures of deep learning, which was RNN in this particular case, and a very specific variant of RNN, which I described as eco-state network or ESN. You would not hear about this particular variant in any other domain, for example, LMP or any other domain, but this was very specific to what became popular in security. And there also it was seen that the detection rate was very high. I'm not comparing the 95% above 98.3% here, because the data was completely different. So you cannot do like an apple-to-apple comparison. But these were the two prominent researchers that set the stage in cybersecurity to start using deep learning over classical machine learning. And what both of these actually proved was that deep learning, at least for the type of data set that they used, was performing much better than any of the classical machine learning in both the terms of recall and also the false alarm rates. Then in 2016 onwards, we started also seeing the evolution of CNN, which is the type of deep learning algorithm that we saw for computer vision. And in this particular case, this also started proving its goodness in terms of malware detection. In 2017, like whatever work that was done in 2015 with the RNNs with for Kanu et al., this experiment was repeated, but other forms of recurrent neural networks was also used, namely like the more popular algorithm that was there in the NLP domain at that point in time were LSTMs, or long short-term memory, and GRUs, which was gated recurrent unit. LSTMs were more on the performance side. GRUs had lesser, like different architectures, so it was more efficient in use, and sometimes used to give equivalent or sometimes even better performance than LSTM in very specific use cases. This becomes very popular in NLP, so they started being applied in cybersecurity just to evaluate if ESN was the best as predicted by that particular research earlier, or these popular algorithms are also good. And they found out like similar to the NLP domain, LSTM is actually more performant in cybersecurity also as compared to the ESN, which is not so popular in other domains. Then in 2017 onwards, we started also seeing different sequence-based data and comparison of different layers of architectures of DNN. And that is where they established that if you compare between DNN, which is like a sequential architecture, to which works on non-recurrent data, to LSTM, which works on recurrent or the sequences of the data. In most of the NLP-based domain, you have found out that the whole motivation of moving to LSTMs and RNN-based architecture as compared to DNN-based architecture was that these were more performant. The RNN-based architectures were more performant because they would preserve the sequence of words as we speak, and that is the sequence of words that gives the language its very meaning. And if you are able to preserve the sequence, then you can get better predictions on the words as you're going to speak next, or classify the sentiment of the words, and it has sort of a prediction or classification or generation sort of a thing. But this was like a rare example where people found out, specifically in the case of security, that DNN-based architectures, which doesn't actually maintain the sequence of these tokens or words, as you may call it, works better than the ones that actually maintain the sequence of. This was like a unique anomaly that was found in cybersecurity, and that's where I put this particular paper. And then in 2018, there were other examples of deep learning which started working on as low as opcode level things. So most of the other were very high level features. There are different types of analysis in malware detection. One is called a static analysis, one is called a dynamic analysis. Static analysis, the ones in which you get a feature directly from the file without making it work like a file, or without executing it, or without seeing what is the behavior of the file. If you actually execute that file, or through some other ways, if you get the behavior of that file, what it's trying to do, that will fall into the category of dynamic analysis. Most of the things that I'll be talking about will be in the case of static analysis. And in static analysis, you have to go deep. You have to go into the deeper structure of the files, maybe in the form of the binaries that it presents, or maybe in the form of opcodes that we talk about. So 2018 onwards, these things started being using at a very, very complex level. And what makes it different from the other applications, that at this particular level, we are talking about binaries, or we're talking about opcodes. No human can read it and understand what is happening around it. So even at that level of complexity, these neural networks can actually go and understand what either file is malicious or a non-malicious file. Now we come to our first part, where we directly apply some of these neural networks, which is in this particular case an NLP-based deep neural network that we talked about, for the purpose of detection of a malware from a Windows PE file. I'll again take a pause and see if there are any questions, and then we'll complete this particular section, and we'll call it a day for this particular session, and we'll complete the other parts and application maybe in some other. So I'm just seeing if there are any questions.
So there are one or two questions if you want to take at this point. Um, how are second generation malware created? Is AI used? If yes, which part of AI is used?
Okay, that's a very interesting question. Question to the I'll answer the first part of question: how is the second generation malware created, and that will also encompass if AI is being used. In fact, in this talk itself, if we go to the third section, that will have a lot of AI to create a malware. Of course, the idea of this talk is not to arm you with things that could be dangerous for the whole society. So we'll not we'll have like specific protection that we have kept in our AI. And if you remove this type of protection, you can actually end up with a real AI-based malware. But today, how second generation malware could be created? Number one is like we talk about encrypted malware, so different types of encryption algorithms. You take a particular malware and you encrypt it with those different algorithms, and even within those algorithms, so suppose if you have an algorithm which is called an RSA, which is a very, very popular algorithm in all the file exchanges that you do over the internet. If you would have got a public key and a private key, most of these things would be coming to you from a RSA based algorithm of encryption. Now you will have one key, which is a public key. You can keep taking different types of public keys, and you can keep encrypting the file. It will give you different copies of that particular malware. It is as simple as that. If you want to just create a encrypted malware, which is not of the quality of the oligomorphic, polymorphic, or metamorphic. Then there are also virus generation toolkit. If you just Google by this particular name as virus generation toolkit, they will also give you some sort of a repackaged malware. I'm not calling it as a pure second generation malware, but some of the malware generation toolkit can have capabilities of creating a second generation malware, mostly of the type of encryption and oligomorphic, metamorphic, and polymorphic malware requires more expertise in terms of human expertise of designing it, but a lot of things that goes into obfuscation, the type of techniques I talked about, inserting junk codes or memory allocation systems. That is what will take into creation of those things. Those could be fabricated through a software-based systems. That level, it will be mostly around lower scalability. You can still create it, but you will have to actually replicate it in terms of the design of those particular systems manually. AI-based systems are now coming up. In this talk, we'll be talking about some of these techniques, but there's no public literature, and obviously no one would leak a public literature if they're actually using AI to develop it. But it would be very naive to believe that there is no AI-based system. If we can do it, no one else can do it. So in the third part that we'll be talking about, we'll be also talking about AI-based system to generate malware-like systems. Again, this will be sort of a simulation. You will not be able to use it to create any malware with the protection that we have kept. But then we'll be talking about defenses for AI-based malware. So if someone is actually creating AI-based malware, how do we defend against those systems? So, very good question. Thank you.
So we have another question in HTTPS. Do we use ciphertext or some other encryption?
No, ciphertext was just an example, just to show like how can you change like one text to another text in terms of visually, but it has the same meaning if you know how to reverse engineer. There are different types of algorithms being used on internet for encryption. RSA is like one of them. So you have for these secure systems, there'll be keys that will be on the servers, and those keys would both on the origin and the destination servers, and those keys would be used to either encrypt that particular message that is being sent, and then at the receiving end, they will be decrypting those messages. So anything, suppose even if you are doing a login into your system, if it is a HTTPS system, that login information, your username and the password that you have entered would actually be encrypted at the end of your receiving servers, and before it reaches, suppose if it's a Google system that you're trying to log in into, before it hits that Google server, all of this thing would be encrypted, and now your username password will go into an encrypted manner to that particular system. And now the destination system, they'll be decrypted back to see if your username matches the username.
Okay, so we have another very interesting. Is, how do various bank servers cope with the increase in cyber threat?
I think that's how do we?
How do the various bank servers cope with the increase in cyber threat to protect customers?
Okay. I can talk about Microsoft systems, how Microsoft systems are depending on the different tenants and the clients that we have. I will not be the right person to talk about specific bank system, but of course, banks is again a financial system, so there is need to have like a lot of different security architectures. In the initial slide, if you see, I have talked about a generic security architecture which deals into the EDR, EPP, and other sort of a system. So I'm assuming they should have something like that, depending upon how big the bank is, how much is the investment into it, and how with the security posture, they would have adopted one or different parts of that particular architecture that I showed earlier.
Okay. In Microsoft, what kind of technology do you use for malware detection? Means, what is your approach? What is the process?
Okay, some of this would be confidential information that I might not reveal in this particular talk, but if you see, go on to the security.microsoft.com or just type Microsoft security into Bing, you will see like a lot of different researches that we have. Or if you go on some of the Microsoft journal for security that we have, or if you search by my name, you'll come to know about a lot of different researches that is public facing or public information. That I think should go some extent to answering your question. But beyond the public information that is available on these resources, I am not free to talk a lot of different internal stuff.
Okay, so we'll take one last question. Probably we'll have to set up another talk to cover the other areas, the other applications. But one last question. This I think might take a little bit of time. Could you elaborate ESN ML algorithms? Why ESN is used in quite often in cybersecurity?
Elaborate on which
ESN ML algorithm.
Okay. So ESN algorithm is actually a type of recurrent neural network, which is called an eco-state network. Since I have not gone into the depth of the RNN itself, it will be difficult for me to differentiate an ESN from an LSTM GRU network. But if you actually go into this is like an LSTM network. If you see the whole problem that was there with the RNN system, why it couldn't scale was because of the vanishing and radio system with the layers that it has. So once information is passing through different sequences and then through different layers, a lot of information couldn't be retained very well at the level of the contextual memory in RNN because of the complex matrix computation that was happening at that particular level. And that is where LSTM was proposed. In this case, LSTM would have like different input gates, output gates, and forget gates. This was like an architecture that was made into how do you manage the contextual memory that a cell has an information to as a context, such that it can make predictions beyond the input that is received. Now, the difference between LSTM, GRUs, and ESTM would actually be linked to how the memory management is done. I'll not go deep into this particular stage, but if some of your instructor and some of the classes you are going deeper into the architectures of RNN, this would be actually a question for that particular.
All right, so we have 5 minutes left. So just a generic question to end the talk to kind of summarize whatever we've been discussing over the last 90 minutes. Where do you see this leading to in terms of the conjunction of AI and cybersecurity? Will we reach a level where AI will be able to detect cyber threats and solve them before it can cause major damage? Do you see it heading that way? Is that the objective of bringing these two technologies together?
That's a very tough question where it is going, but this, as I described, malware detection and malware development is our largest. Still, there are resources being employed towards malware creation and malware attacks. you will have to put so much resources into malware detection and malware defense also. Now the problems start becoming non-linearly complex because even if there is one attack somewhere and you create a defense against that particular type of attack, once you do not see the defense attack surfacing anymore, you cannot shut down the defenses against the attack. So where malware developers can keep changing their modus operandi or the type of malware that they have, you cannot let your defenses down against the things that they have even passed on in your perception they have passed. Because the moment you bring down your defenses on that particular film, they will actually use a trivial previous malware to perpetuate a similar attack without compromising the whole ecosystem. Now we talked about AI being used into malware development, but there are also ways where simpler AI or even complex AI being used to propagate these type of attacks, or not just to develop malware but also to use the modus operandi or into some other areas of attacks. We covered a lot of different threat posture. In each of these, we talked about AI being used for the defense. There is also AI being used or could be used to actually perpetuate it. Now, a defense scenario becomes more complex than an attack scenario because you do not know where the attack is going to go. Similarly, like if you are playing game of cricket, you can get out on any of the ball, but you have to be a very good batsman to score that particular. So that is the same case in AI also. So that story of rat race will continue, depends upon how much resources is going to come into the development of malware. You have to spend non-linearly into the defense of malware. But malware is not the only problem. There's a lot of different security problems. The other type of problem that I could see into the future for applications of AI into defenses, number one is the explainability side of things. Currently, signature matching technique, as everyone recognizes, is very explainable. Even classical machine learning based things, you ask about like how it is working. Many of the people will be able to explain you that these are the important features, and based upon these features, we say that we have made this particular prediction. Since most of these features are coming from the domain expert, in domain expert language, you can actually explain what is happening and why your malware model is able to classify this particular malicious of it. But the whole idea of deep learning is that the systems are actually creating the whole features themselves in a very complex mathematical model, which is not only difficult for humans to create by themselves, but also the humans to understand, which gets into the area of domain, which is called as explainable AI. In other domains, it may not be so much required, but in the case of things where security is involved, and security being a conservative field, you have to be very good at explaining what we have seen these aspects coming up into area of safety and hazards. For example, in case of self-driving cars, where explainable AI is the need of the hour, despite the fact that the models are complex, and more the model is complex, the more difficult it is to explain. That is another area of AI in cybersecurity, which I see is the future of in the research that is going on these days. Then there is another area which is technically called as model. So we talked about a lot of things around deep reinforcement learning. Here we talk about an agent which is learning a particular policy to do a particular thing. In this particular case, either generating an AI-based malware or defending against it using orchestrations and normalization. But there are other techniques in which agents can actually work in collaboration. So if I have to assume a particular swarm or a drone-based attack that we are trying to do on a particular very well-defended missile defense use. So there will be not one particular drone, there will be multiple drones that will be working in conjunction. One will be confusing the missile defense system, the other would be doing like a random attacks on some other systems, such that the missile systems could be, defense system could be diverted over there. And then there will be finally the set of drones that will be coming in, attacking the main radar or something. These are called very coordinated MERL systems, or multi-agent reinforcement learning systems. So similar type of things I see happening to cybersecurity also, where there'll be coordinated swarms of malware that will be talking to each other and trying to see what are the things things do similar things that an army of very intelligent humans or things will be doing. There are a lot of things that I see. I have actually a complete paper on it if you find by my name, and in the end of the fourth section, I am actually keeping something that will talk about a lot of different applications or advanced applications in AI that I see currently the research is either focusing or should focus to actually keep this field very live.
Okay, so we have come to the end of the session, but we'll come back to go through the rest of the applications. Now, for all the students present in the room today, right? See, learning data science is one thing. You learn SQL, you learn Python, you learn Power BI, and you learn all of these things. But the reason why we do talks like these every week is for you to understand when you finally get that job, right? When you actually go into the industry, what are the different ways, what are the different domains in which you take all these learnings and apply it, right? It's not just about learning Python and SQL. So that is the reason why through these different Odin talks, we will be talking about how is data science and AI applied in cybersecurity? How is it applied in the banking segment? How is it applied in pharmaceuticals or across different elements, right? So some of you are just starting out this course. This is probably your second week or your third week or your first week. Um, you might find it difficult to understand some of the things that were discussed here, but this is a very good exposure, right, and awareness opportunity for you. Once you finish a few more weeks in the program, come back to this session. All these sessions will be available for you on the LMS recorded. When you kind of understand more of these terminologies, as you learn more, and then come back to this talk and watch it again, then you'll get a lot more clarity about all these aspects, right? So um, data science AI has applications across different domains, and through these Odin talks, it is an attempt to help you understand all these applications, right? So there is so much more to discuss on this topic, on the applications of AI in cybersecurity. Both of these are two huge areas, and combining them is really difficult, especially to encapsulate all of them in 90 minutes. But we will have a series of these sessions more where you'll understand each of these elements in detail again, right? For those of you, if you're coming from cybersecurity background, or if you aspire to get a job in to work in this area, then this can be one of your start points. So that's it for now. We will come back again with more Odin talks, more awareness sessions, more domain specific topics in the coming weeks. Dr. Mohit, thank you so much
for
for
spending
spending
time
time
with
with
us.
us. Um, Thank you so much for sharing all that information, and looking forward to having more sessions with you. Thank you so much.
Thank you. Pleasure being here.
Um,
Uh,
Srinivas, over to you.
yes, thank you, ma'am. Thank you so much. And yeah, it was a great session, and it's very thanks to you, Dr. Mohit. Yeah, and that's it, guys. So we'll meet again in the next Open Talk session. So feel free to reach out to us if you have any doubts. Okay. Thank you.